Hey, everyone! Welcome back to the channel. Today, we have some mind-blowing news from the cosmos. The James Webb Space Telescope, JWST, is at it again this time. It's found data that could potentially shake up everything we know about the universe. Specifically, its findings contradict the long-standing reionization models that explain how our universe transitioned from the cosmic dark ages into a world filled with stars and galaxies. What does this all mean, and how could this data challenge our fundamental understanding of the early universe? Stick around, because we're diving deep into the science. To understand the significance of this discovery, let's first talk about reionization models. These models describe a period in the universe's history about 400,000 years after the Big Bang, known as the Epoch of Reionization. During this time, neutral hydrogen in the universe was ionized, meaning that it was split into protons and electrons by intense radiation. This period marks the universe transitioning from a dark, cold state into one filled with stars and galaxies. For decades, astronomers have relied on these models to explain how the first stars and galaxies form. They've used them to interpret the light from distant objects, measuring how much radiation was needed to ionize the hydrogen and create the universe as we see it today. But the latest findings from the James Webb Telescope could be throwing these models into question. The James Webb Space Telescope has been scanning the farthest reaches of the universe, looking at galaxies formed during the early stages of the universe's development. Recently, it detected some unusual patterns in the light from these distant galaxies that don't match the predictions made by current reionization models. Specifically, the telescope discovered one possibility is that the early universe was populated by types of galaxies or sources of radiation that are currently unaccounted for in our models. Another theory is that dark matter or some other unknown force played a bigger role in the reionization process than we realized. Either way, this discovery opens up a treasure trove of new questions about how galaxies form and evolve. So what happens next? The JWST's findings have already sparked a new wave of research in astrophysics. Scientists are now diving deep into the data, developing new theories and models to explain how these galaxies could exist and shine so brightly in a time when the universe was supposedly still in a dark, neutral state. The scientific community is also eagerly awaiting more data from the James Webb Telescope. By studying more galaxies from this early period of the universe, astronomers hope to get a clearer picture of what's going on. Are these galaxies an anomaly, or are we really missing a huge piece of the cosmic puzzle? One thing's for sure, this discovery is going to keep scientists busy for years to come. The implications of this discovery are profound. If we need to rethink reionization models, then our entire understanding of cosmic history, how the universe grew from a primordial soup of particles into the complex, star-filled cosmos we see today, could be incomplete. It may even change how we look at phenomena like black holes, dark matter, and the formation of planets. More broadly, this discovery serves as a reminder that science is always evolving. Every time we make a breakthrough, it forces us to reconsider what we thought we knew. The James Webb Telescope is giving us a clearer view of the universe, but it's also showing us that there's still so much we don't understand. To further grasp the importance of reionization, we need to understand its connection to the cosmic microwave background, CMB. The CMB is the afterglow of the Big Bang, a faint radiation that fills the universe and offers us a glimpse of its infancy. Scientists have used CMB data to infer many details about the early universe, including the timeline of reionization. However, the recent JWST findings indicate that our interpretation of the CMB might need to be revisited. If the galaxies are more luminous and plentiful than expected, it could mean the reionization process started earlier or occurred differently than current models predict. This discovery makes us question how well we've connected the dots between the CMB and the era of reionization. One of the main drivers of reionization is believed to be early galaxies. These galaxies, forming just a few 100 million years after the Big Bang, emitted ultraviolet radiation powerful enough to strip electrons from hydrogen atoms, thus ionizing them. The problem is that current models suggest there shouldn't have been enough galaxies or stars to fully reionize the universe as quickly as we observe it today. What's groundbreaking about JWST's data is that it's showing far more galaxies than anticipated during this early period. These galaxies, while still very young and small compared to today's giants, seem to have been far more influential in cosmic evolution than previously thought. This discovery suggests that the engines of reionization were much more efficient, and this could drastically alter our understanding of how the universe became transparent to light. Before reionization, the universe experienced a period often referred to as the Cosmic Dark Ages. This was a time when there were no stars or galaxies, and the universe was filled with neutral hydrogen that absorbed light. The transition from this dark era to one filled with light is what the reionization models have tried to explain. However, the JWST findings are suggesting that this dark period may have been shorter or more complex than we've previously believed. The abundance of early galaxies suggests that star formation could have started earlier than expected, possibly lighting up the universe sooner than our models predict. This is another piece of evidence that we might need to adjust our understanding of the timeline of the universe's early years. Quasars, the incredibly luminous centers of galaxies powered by supermassive black holes, are also believed to have played a role in reionization. Their powerful jets of energy can ionize large regions of space, contributing to the clearing of the cosmic fog. While quasars are a known factor, the JWST's new data could mean they played a different role than previously thought. Perhaps they were more common or more powerful in the early universe than our models suggest, contributing more energy to the reionization process than previously believed. This opens up new questions about how quasars formed and evolved alongside the early galaxies JWST is now revealing. Another intriguing aspect of the JWST findings is the possibility that dark matter could have played a bigger role in the reionization process than we currently understand. Dark matter, an invisible form of matter that makes up about 85% of the universe's mass, is believed to have influenced the formation of galaxies and large-scale cosmic structures. If dark matter interacted in unexpected ways with the early galaxies, it might have helped accelerate reionization. For example, dark matter could have clumped together in a way that facilitated the formation of massive luminous galaxies earlier than expected. This is speculative for now, but the JWST data gives us a reason to explore these possibilities more closely. Another question raised by the JWST findings concerns the rate at which stars formed in the early universe. For reionization to occur as quickly as JWST's data suggests, star formation must have been incredibly efficient during this time. This means that early galaxies must have been producing stars at a much higher rate than models have accounted for. This discovery not only challenges our understanding of how stars form, but also forces us to rethink the conditions in which the first stars were born. Perhaps the environments within these early galaxies were far more conducive to star formation than we previously believed, which could alter our understanding of stellar evolution. Supernovae, the explosive deaths of massive stars, play a significant role in the evolution of galaxies and the universe. They produce heavy elements and can trigger the formation of new stars. In the context of reionization, supernovae could have contributed to the energy needed to ionize the universe. JWST's discovery of these bright early galaxies raises questions about how frequent supernovae were in the early universe. Were there more supernovae than we expected, releasing bursts of energy that helped accelerate reionization? Understanding the role of these stellar explosions in the early universe could be key to updating our models. One aspect that JWST's findings may shed light on is the nature of the first stars, also known as population III stars. These stars are thought to have been massive, hot, and short-lived, and they would have produced a tremendous amount of ionizing radiation. However, no direct evidence of these stars has yet been found. If JWST has detected galaxies with an unexpected amount of ionizing radiation, it could be a sign that these population II stars played a bigger role than previously believed. Alternatively, it could suggest that other types of stars or stellar populations were involved in reionization, adding complexity to the story of how the universe became transparent. The JWST findings also have major implications for our understanding of how galaxies evolve. If early galaxies were brighter and more numerous than expected, it could mean that the processes driving galaxy formation were much more efficient in the early universe than our models account for. This raises questions about the factors that influenced galaxy growth and development during this period. Were early galaxies more prone to mergers, or did they grow by accumulating gas and dust more rapidly? These are questions that scientists will need to answer as they continue to analyze the JWST data. On a broader scale, the JWST's discovery has significant implications for cosmology, the study of the universe's origin, structure, and ultimate fate. If the reionization models are incomplete or incorrect, it could change how we understand the expansion of the universe, the formation of large-scale cosmic structures, and the role of dark matter and dark energy. This discovery could lead to revisions in the standard cosmological model, which is the framework scientists use to describe the universe. Such revisions would not only affect our understanding of the past, but could also impact predictions about the future of the universe. The JWST's ability to observe the early universe with such precision is a testament to the importance of advanced technology in scientific discovery. Without the JWST, we wouldn't have the detailed data needed to question long-standing models like those of reionization. This underscores the importance of continued investment in cutting-edge observational tools. As technology improves, our understanding of the universe evolves, and discoveries like this remind us of the importance of looking deeper into the cosmos. Another intriguing possibility raised by the JWST data is that there might be unknown sources of ionizing radiation in the early universe that we haven't accounted for. While galaxies and quasars are the primary known sources, the unexpected brightness of these early galaxies suggests that something else might be contributing to the ionization process. Could there be entirely new types of astronomical objects that emit large amounts of radiation? Or could there be interactions between galaxies and dark matter that produce ionizing effects? These are just some of the questions that arise as we try to reconcile JWST's findings with our existing models. This opens up the exciting potential for discovering completely new phenomena in the universe. Before the James Webb Space Telescope, the Hubble Space Telescope was our most powerful tool for observing distant galaxies. While Hubble provided groundbreaking insights, it was limited in how far back in time it could observe. The JWST, with its infrared capabilities, allows us to see even further back, to when the first galaxies and stars were forming. This enhanced view is what's making these new discoveries possible. JWST's ability to detect faint galaxies and other cosmic phenomena from the universe's earliest epochs gives scientists an unprecedented look at the processes that shaped the cosmos. The contrast between Hubble's and Webb's data highlights how much more we're learning and how previous assumptions are now being challenged. One of the most exciting aspects of JWST's findings is how they're driving collaboration in the scientific community. Astrophysicists, cosmologists, and other researchers are coming together to make sense of this new data, sharing their insights and developing new models to explain what we're seeing. This collaborative effort is essential, as no single scientist or institution can unravel the mysteries of the universe on their own. Teams from all over the world are contributing their expertise, using not just JWST, but also ground-based telescopes and computer simulations to re-examine the early universe. This cooperative approach is a powerful example of how science advances through teamwork and open inquiry. The JWST's discovery is a sign of how much there is still to learn about the universe. We've barely scratched the surface of what this telescope can reveal, and already it's challenging some of the most fundamental ideas in cosmology. As more data is collected, we can expect even more surprises. In the coming years, the scientific community will likely update its models of cosmic evolution, reionization, and galaxy formation based on what JWST continues to uncover. This is just the beginning of a new era in astronomy, where every discovery pushes the boundaries of what we thought was possible. The universe is more complex, dynamic, and mysterious than we could have imagined, and we're only starting to unravel its secrets. One area of research that JWST's findings could impact is our understanding of the cosmic web, the vast interconnected network of galaxies, gas, and dark matter that makes up the large-scale structure of the universe. Early galaxies form along these filaments of dark matter, which act as scaffolding for galaxy clusters. The discovery of more luminous and abundant galaxies in the early universe suggests that the cosmic web may have played a more active role in star and galaxy formation than previously thought. If the cosmic web had denser or more efficient structures earlier in the universe's history, it could have helped funnel gas into galaxies more rapidly, leading to the accelerated formation and ionization processes we now observe. The JWST might provide valuable clues that help us refine our models of how the cosmic web evolved and influenced the growth of galaxies. The discovery of more galaxies in the early universe raises another interesting question. How did supermassive black holes grow so quickly? Many of these early galaxies likely housed black holes at their centers, and if these galaxies were forming stars at a rapid pace, they could have also been fueling the growth of their central black holes. This could challenge our current understanding of how supermassive black holes formed and grew. If they were already present in the earliest galaxies, it could mean that black hole formation was much faster and more efficient than we thought. The JWST's ability to peer into the distant past could give us more insight into this mysterious aspect of cosmic evolution. Another fascinating question raised by JWST's findings concerns the presence of heavy elements in the early universe. Heavy elements like carbon, oxygen, and iron are formed in stars and spread throughout the universe when those stars explode as supernovae. However, the early galaxies observed by JWST appear to contain more of these elements than expected for their age. This suggests that either star formation and supernovae were happening at a much faster rate in the early universe, or that our understanding of how these elements were distributed needs revision. The unexpected abundance of heavy elements could provide clues about the conditions in which the first stars formed and how galaxies enriched themselves with these vital building blocks of planets and life. One factor that could help explain the JWST's findings is the role of feedback mechanisms in galaxy formation. Feedback occurs when stars and black holes inject energy back into their surroundings, affecting the formation of new stars and the behavior of gas within galaxies. If feedback processes were more efficient in early galaxies, they could have accelerated the reionization process by helping to ionize surrounding hydrogen. Welcome to Blessovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valuable. Don't forget to leave your comment.